This is standard 8GA4. Here we're going to explain that one two-dimensional figure is similar to another if one can be mapped onto the other using a sequence of rotations, reflections, translations, and dilations. Then, given two similar two-dimensional figures, we will describe a sequence of transformations that can prove their similarity. First off, we know that rotations, reflections, and translations. Let me underline them for you so we can see these so we understand what we're talking about. Rotations, reflections, and translations are all congruence transformations. Rotations, Rotations, reflections, and translations are all congruence transformations. Whenever we are doing those, we're going to create a figure that is exactly like another. The two figures would be congruent. Dilations create figures that are similar. And we've talked about this before. Let's talk about dilations just real quickly. If you dilate something by a scale factor that is greater than 1, you're going to make the figure bigger. The new figure will be bigger. The image will be bigger than the pre-image. But what you will know is that, let's say this is your pre-image, and this is your dilated by scale factor, say 2. It's going to have the same angle measures, same corresponding angle measures. The sides would be proportional. The figures will be the same shape. But if you're dilating by a scale factor greater than 1, the one you're going to create is going to be bigger. What if you have a scale factor that is between 0, let's say it's between 0, scale factor is between 0 and 1. In other words, a fraction that isn't negative. If you do that, the figure you're going to get is smaller. You would be creating something that's smaller. Let's say you started with this. This was your pre-image, and you dilated by a scale factor of 1/2. This would be 1/2 the size of this one. What if your scale factor is 1? If your scale factor is 1, your two figures would be the same size because you're not blowing one of them up. You're not changing the size of any of the sides. So we've got 3 congruence transformations: rotations, reflections, and translations. And then if we use a dilation, then we can prove that the figures are similar. Okay, now let's look at this. And remember, when we talk about similar, we'd be looking at a situation like this. Let's say this side is 4, this side would be 8. Let's say this side is 5, this side would be 10. If we look at these two, 2 is to 1, this side is to that side, as 8 is to 4, these corresponding sides, as 10 is to 5. If I reduce these, this is 2 is equal to 2 is equal to 2. These two are proportional. Their sides are proportional. Okay, so let's show how we can explain that two figures are similar. If I start with these two figures and I say, I want to prove that this one's similar to that one. Remember, we can use a series of transformations. The congruence ones are translation, reflection, and rotation. The one that will make it bigger or smaller is our dilation. These two are not the same size. Let's find two corresponding sides and see how much I'd have to dilate shape A by to make it the same size as shape B. This side here is 1, 2, 3 units long. Let's see how long its corresponding side is. See how these are both the long side on these trapezoids? 1, 2, 3, 4, 5, 6. If this side is 6 and this side is 3, if I'm trying to make it from shape A to shape B, what I could do is, why don't we dilate shape A by a scale factor of, what scale factor would I need to use if I'm trying to make this figure the same size as this one? If I'm going from 3 to 6, what do I need to multiply by? by 2. So we're going to dilate shape A by a scale factor of 2. Let's do that first. Now, if we're dilating from the origin, all we have to do is take each one of the vertices, the coordinates for each vertex, and multiply it by 2. This one's at -1, 3. If I multiply that by 2, I would wind up with distributive property sort of thing, -2, 6. Okay, so let's plot -2, 6. -2, 1, 2, 3, 4, 5, 6. This is where this point moves to. Now let's move this point. This point is currently at -2, 5. If I dilate it by 2, I'm multiplying it by a scale factor of 2. 2 times -2 is -4. 2 times 5 is 10. -4, 10. Okay, so we're at -4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, that's where this point goes to, right? Let's get this point here. This point is at -3, 5. If I've got -3, 5, let's multiply it by 2, dilate it by a scale factor of 2. 2 times -3 gives us -6. 2 times 5 gives us 10. -6, 10. -6, and here's our 10 right there, huh? -6, 10. All right. And then let's do this point. -4, 3, okay? -4, 3. And if we dilate that by 2, we've got 2 times -4 is -8. 2 times 3 is 6. -8, 6. Out here, -8, go up 1, 2, 3, 4, 5, 6. Okay, I'm going to draw this for us so we can see it. This is what it's going to look like after we've dilated it. Okay, see how we've made it much bigger, twice the size as it was, and it moves away from the center of dilation. That's what happens whenever you're dilating a figure on a coordinate plane. Now, what I need to do is I need to get this one on top of this one. If I can map it on top of this one, then I can prove that these two are congruent. I can prove these two are similar because I've dilated one. First, if you dilate one, if you can dilate it and then map them on top of each other, then they are similar. Okay, so let's figure out how we can get this one to where it is here. We need to figure out how to map it on top of this one. What if, okay, now look, see how we got the small side on the top here, small side on the bottom there? What if we reflect it over this x-axis? Wouldn't that put this small side on the bottom? Let's reflect it over the axis. This point is 1, 2, 3, 4, 5, 6 above, so it's going to be 6 below. 1, 2, 3, 4, 5, 6. That point would be there. Let's take this point. This is where it's 10 above. It's going to be 10 below. So let's take this down to 10. Which one am I on? -4 down to -10. Okay, that's where that point would be. Okay, this is 10 above, so we're going to come down its line. It should be at 10 below. And this point is 6 above, so on the same line, we're going to go 6 below. And let's draw our figure again. And see where we are. What did we do here? We have reflected over the x-axis, haven't we? And now we're drawing our new figure so we can see where it is. This is where we are now. And what did we do to get there? We reflected the figure over. And you always tell, when you're doing a reflection, you got to tell it what you're reflecting over. over the, and where would be, you would be folding it, x-axis. If you fold it, this would be on top of that, over the x-axis. Now let's see what we can do to put this one on top of that. Okay, to do that, I need to move this point to here, not to here, right? But all the way over here. If I move this one, I'm going to have to go right 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so let's move this one 10 units right. That would put it right here. Okay. Let's use this. Let's move this point 10 units right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That puts that point right there. 10 units right. 1, 2, let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right there. And then 10 units right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? And see how we have translated this unit, this figure here right on top of this. If I can map it on top of this one, then I can prove, if I've dilated it and then I've used congruence transformations to map it on top of it, then I have proven that these two are similar. What was that third step? We translated the figure how far? 10 units. In which direction? Right. Okay. Now, notice, what did I have to do to prove that this figure was similar to this one? I needed a dilation, and after I dilated, I can use as many different congruence transformations as I need to move it, to place it on top of this one. And when I do that, I've proven that these two are similar. If I could do a dilation and then a reflection and a translation, and even if I needed a rotation, I would be proving the two figures similar. Because when two figures are dilations of each other, then we know that the figures are similar. How do we prove them similar? It involves what? A dilation, and then a congruence, one or more congruence transformations, right? That's how you can prove that two figures are similar. Okay, we're going to put a dot there, transformations. Now, let's come down here, because remember on our standard it said given two similar two-dimensional figures, describe a sequence of transformations that can prove their similarity. We actually did that right here. I showed you that. I showed you that if we used a dilation and then the congruence transformations, the two were similar because I could map them on top of each other. Now we're going to be asked to prove that these two are similar by doing just that. Okay, first off, we notice they're not the same size. Let's find two sides that we can compare. AC here is 1, 2, 3 units long, right? This is its corresponding side. It's 1, 2, 3, 4, 5, 6 units long. So if I start with ABC, how much would I have to dilate it by to get this figure? To get from 3 to 6. Gotta multiply it by 2, right? So we're going to use a dilation. Whenever you're proving two figures are similar, you start out by dilating one. So let's dilate, and let's tell what we're going to dilate. We're going to dilate triangle ABC by what scale factor? By a scale factor of 2. How do I know it's 2 and not 1/2? Because I start with this one, the 3, and I got to multiply it by something to get to the 6. If I'm starting with this one, to get to that one, get from the 3 to the 6, I multiply by 2. If I were starting with the big one and making it smaller, then I would be multiplying by a fraction. But I'm starting with the small one and making it bigger, so I multiply by a number greater than 1. Okay, so let's go ahead and do this, and let's see where our coordinates would be. Where is A? Let's check to see where A is. A is currently at -1, -1, 2, 3. if it's at -1, -3, and you multiply that by 2, that's our dilation, our scale factor, then I would have -2, -6. Okay, so let's put this in. -2, -1, 2, 3, 4, 5, 6. Okay, that is where your A prime is. That's what we've created. We went from A to A prime. Okay, let's do B. B is at 1, 1. If I dilate that by a scale factor of 2, then B prime is going to be 2, 2. Okay, 2, 2. There's our B prime. And C is currently at 2, -3. So let's dilate it by a scale factor of 2. That means we multiply these coordinates by 2. Whenever we're dilating from the center of dilation at origin, we can do that. 2 times 2 is 4. 2 times -3 is -6. So that would be at 4, -6. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Okay. Now I'm going to draw that one so we can see where our triangle actually is located. So we can continue from there. We are going from our A prime up to our B prime. We're going from our B prime to our C prime, which I didn't label, sorry about that. And then we're going from our A prime over to our C prime. That's what our triangle looks like now. Okay, I still need to map it on top of this one to prove that these two are indeed similar. I've made it bigger. I can see the two of them are about the same size. I started with this one. I dilated it. That's your first step whenever you're trying to prove two figures are similar. I dilated it. Now, let's see what we can do. Notice how the pointy end, the B, is up here at the top, but down here it's at the bottom. Won't I need to flip this over? So let's flip this over. Let's flip it, in fact, over the x-axis. If we flip it over the x-axis, it's going to put the pointy end down there. When we reflect it, when you flip it, it's called reflected. Okay, so we're going to reflect over what? This x-axis. Reflect the figure. Over the x-axis. Okay, so the way we do this is we count to see how far we are from this line of reflection. B prime is 2 points above the line of reflection, so it's going to be 2 points below. It's our B. Okay, A prime is 1, 2, 3, 4, 5, 6 below, so it's going to be 6 above. 1, 2, 3, 4, 5. Wait, let's do this again. 1, 2, 3, 4, 5, 6. Okay. And then this point here is 1, 2, 3, 4, 5, 6 below. It's going to be 6 above. 1, 2, 3, 4, 5, 6. Okay, so if we're dealing with that, let's draw our triangle so we can see where it is. I'm kind of sketching here so we can see what we're looking for. Am I in the right place? No, right there. Right there. No. Hold on. Let's see where B is. 2 above, 2 below. B's right there. Okay. And then on this one, go from there to here. Okay. Now, how can I put these two on top of each other? Or I think I got one of these off. Okay, now I need to move this over. No, I'm going to need to reflect this one again. Okay. All right. What we'll need to do is do another reflection, because you see how this is kind of coming in a different direction and that's like that. We're going to need to reflect this now over the y-axis, okay? Let's reflect it over the y-axis. Let's see where it would be. If I reflect this over the y-axis, I'm 2 from here. I'm going to be 2 over there. Here I am 1, 2, 3, 4 on the side. I'd be 1, 2, 3, 4 over there. And this is 1, 2 from the axis, so it'd be 2 from there. Now I have put these two straight on top of each other. I've reflected them so they are right on top of each other. I've mapped them on top of each other. I'm going to try to sketch this, go over the lines that I've got. What I've got is right there. Let me write this down, what we actually did. The last step is that we reflected it. Reflect the figure over the y-axis. What did I do? I started with this figure here. I dilated it. If I dilate it, I'm proving that the two are similar. I dilated it by a scale factor of 2, made it twice as big. I reflected it over the x-axis. Then I reflected it over the y-axis. You could probably do the same thing by rotating this 180 degrees. You could try that. But either way, I mapped one on top of the other using a dilation and 2 reflections, and I've proven that the two figures are therefore similar.